Hello, we are live. Welcome to Starry Nights Live. My name is Kieran, and my co-host today is Matthew.
Hello, everyone.
We also have our two moderators tonight. We have Abby and Zena, who will be taking care of the chat for us. So, big shout out to them. Thank you very much. And tonight we also have a special guest, Marcus Cohen.
Yep.
He is a fifth-year maths phys student at SFU, correct?
Yes, that is correct.
Welcome, Marcus. We're going to start tonight with a little presentation from Marcus, a little bit something different. He's going to show us some of his research he's been doing at SFU. So I'm going to start with a bit of an introduction. Marcus, how long have you been interested in astronomy?
I've always found it kind of interesting growing up, but I really got engaged with it over the past 2-3 years up here at SFU.
Right, and you're not an astronomy major, you're a mathematical physics major.
Yep.
And now that you're doing astronomy, I bet you're just doing a lot of programming, right?
Yeah, that's pretty accurate. I mean, I'd say 90% of my time or more on astronomy is all programming.
Right, so you told your teachers you loved math and you ended up programming. What a ride. Yeah, so why don't you tell us a little bit about the research you've been doing? We've got a little presentation that you've set up. Let's take a look.
Yeah, so for the past 2 summers, I've been doing some research on galaxy quenching with my supervisor, Joanna Wu. So I put together some of the results and background just to share with everyone today. Do I just click on here to make it go?
If you go to Chrome.
There it is.
You got it.
Perfect.
Okay. So first question, what is quenching? Why don't you take it away?
Yeah, that's a pretty good question to start with. Galaxy quenching is just when a galaxy shuts down a star formation. That doesn't necessarily mean that no stars are being formed, it just means that they're being formed at a really slow rate.
So a galaxy has a lot of stars forming in it, and then suddenly, or at some point in time, it has a lot less stars forming.
Yeah, exactly. It's usually not a sudden change when it goes from lots of stars to none.
Mm-hmm.
It's more of something that happens gradually over time.
Got it. So there's only old stars, nothing new being born.
There will be a few young stars, just not many.
Got it.
Yeah, so I have some examples of star forming and quenched galaxies. Any galaxy that isn't quenched, we just call it star forming. These are also known as spiral galaxies. I'm sure everyone who watches these streams have seen a ton of them. I have 2 examples on the bottom left there. Quenched galaxies, though, are also known as elliptical galaxies. Again, I'm sure everybody's seen many of those examples as well. So the main question that we're looking into is how... Oh, sorry, getting mixed up here. How are we looking into galaxy quenching? We're actually studying galaxies in a computer simulation instead of real galaxies that we'd see with observatories just like this one. So the simulation we're using is called Illustris TNG.
What does TNG stand for?
Good question. The next generation, just like Star Trek The Next Generation. I'm sure many people are thinking that right now. So Illustris TNG, it is the second set of simulations, a sequel, if you will, to a set called Illustris from years ago. They simulate the entire universe from the Big Bang to today. They ran a bunch of simulations in different sizes. The one we're studying is called TNG 100. You can see it in the middle of that picture up there. Not only does it simulate the universe, it also simulates a ton of galaxies in it, which we can look in and see them in a ton of detail. To give you an idea of how big these things are, the TNG 100 simulation that we're studying has 73 terabytes of data. So there's a lot there to look at.
I feel sorry for the graduate students who had to analyze all that data and compile it.
Oh yeah, I can't even think of how big a job that is.
Remember, if you want to be an astronomer, you have to be okay with a lot of programming.
Yep. If you want more information on the simulation, I'd recommend checking out tngproject.org. They have a ton of really cool videos and pictures on there.
I think you can zoom through it in 3 dimensions, is that true?
Yeah, they do have a feature to do that. I think you might need to sign up and make an account on their website, though.
Right, but I think you can watch a YouTube video of people doing it potentially.
Oh, I'm sure if you YouTube it, it will come up.
Right.
Marcus, I was so excited when you were chatting with us about this a little bit yesterday because the Illustris simulation, like the Illustris 1.0 version, we show a video of it in the full dome version at the H.R. McMillan Space Center. as well. So when it starts from darkness and then you have the material start to collect together. So I'm really excited to also see like an updated version of this, especially one that's 3D interactive. That's amazing.
Yeah, I definitely recommend searching that up when you get home. Just go to Illustrious, or if you Google Illustrious TNG, it will show up. It should just be on the top header of that website. It's really neat.
So what is this video you're showing us right now?
This is just an example of a couple galaxies evolving over a pretty large period of time on there. I just want to show this to demonstrate really how far in the past we can see with these galaxies. You can see a bunch of them spinning around right now. A bunch of them are merging. It's just a really incredible tool for us to use where we can see how these galaxies change over hundreds of millions of years. Compared to when we look out in the sky, we can only see galaxies at a fixed point in time. We're not seeing them evolve over their entire lifespan. Alright, moving on to the next part. How does quenching happen? One clue we have from real life is we know that galaxies with dense cores tend to quench faster. We know this because when we looked at quenched galaxies, they all have dense cores, whereas star-forming galaxies have diffuse cores. They're not as dense. So then the question is, why do some galaxies evolve to have denser cores than others? So one thing my supervisor Joanna looked at with her colleague Dan Walters a few years back is something called the gas angular momentum. When we talk about the angular momentum of a galaxy's gas, which I call AM here just because it's a bit of a mouthful, it tells us how gas is moving around a galaxy as it falls in. So if we say that the gas has low angular momentum, we're saying that it's falling pretty much straight at a galaxy. And the hypothesis there would be, does that gas end up in the galaxy's center? Whereas if a galaxy has, yeah, there you go. If a galaxy has high angular momentum in falling gas, it's spinning around the galaxy as it falls in. It's not just coming in straight in. And the theory there would be that it's going to end up on the outskirts of a galaxy.
Okay, so if you don't have a good angular momentum, you just fall straight into the core, like right into the center of the galaxy.
That's the idea, yep.
So it's the exact same. If a satellite loses its angular momentum, it'll fall straight down to Earth. Well, almost straight down and crash into Earth instead of maintaining its orbit around the edge, like this gas might, kind of spinning around the galaxy, correct?
Yeah, exactly. In this case, though, when we say the high angular momentum gas, it still is falling in.
Mm-hmm.
It's just rotating much more and probably falling a bit more slowly.
Got it, understood.
So what Joanna and Dan found is that the idea of the gas with low angular momentum falling to the galaxy center is true, because we see that corresponds with really fast core growth. It creates dense cores, which as we saw earlier will lead to fast quenching. Whereas galaxies with gas falling in with low angular momentum, with high angular momentum I mean, they don't grow to have as dense cores, which tells us that the gas is probably ending up on the outskirts of the galaxy, forming stars there instead. And that leads to slow quenching. Alright, so one of the questions that I've been working on with Joanna is, does the angular momentum of gas falling into a galaxy change as it moves closer and closer to that galaxy? And why does that happen? One answer we found to this is it depends on the direction that the gas is falling into a galaxy in. If it's falling in so that it's parallel to the galaxy's disk, the angular momentum tends to not change too much. It stays roughly the same. So that's just the example on the left here. But on the right, if the gas is falling in perpendicular to the disk, it tends to lose a lot of its angular momentum, so we'll go from spinning around the galaxy to falling in a lot more straight.
So to draw a parallel there, on the left you got an example kind of like if something's spinning around the equator of the Earth, and
Yep.
on the right you got an example as if it's spinning from the North Pole to the South Pole, and it's much more stable orbit if it's going around the equator kind of thing.
Yeah, exactly.
And that's probably why, as a parallel, most of our satellites tend to orbit around the equator because it's easier. You don't need as much energy to keep them in orbit. So it's the same with gas orbiting around a galaxy. Same kind of principle?
I believe so, yeah.
Got it. Okay.
Yeah, so that's our answer to that question. It can depend on if the gas is falling into it parallel or perpendicular to the disk. Obviously, this isn't the only factor that can affect if the angular momentum is going to change, but it's just one of the things we found. Right, so second question we looked at is, what determines if that gas has high or low angular momentum in the first place? And one answer we found for that is it depends on the location of a galaxy. What we mean by this is when we zoom out and look at the universe as a whole, we see something we call the cosmic web, which is what we'd call the structure of the universe. You can see this in the images of TNG on the right here. You can see it almost looks like a giant web with a bunch of different strings, what we call filaments, connecting it. All these filaments, they're made up of mostly gas and dark matter that will flow along them.
So what are the really bright spots in those filaments?
That's showing where they are the most dense.
So is there a lot of galaxies there?
There will be a lot of galaxies there, but I believe most of this comes from dark matter.
Oh, okay, so
Yeah.
dark matter means stuff that's not glowing, things we don't see through a telescope, basically.
Yeah.
Oh, okay.
And these filaments are where we find all the galaxies. And we know that gas flows along these filaments and falls onto galaxies. So the question is, what properties of these filaments could affect how the gas falls onto the galaxies? So what we looked at is, if a galaxy is in a filament, is it in a big thick filament or is it in more of a thin one? And we also wanted to see if that filament is really dense with gas or very diffuse with gas, where it doesn't have a whole lot of supply there. We did find a relationship with this. We found that galaxies that are in thick and dense filaments, they tend to have gas that falls in with really high angular momentum, whereas galaxies in more thin and diffuse filaments have gas that falls in with low angular momentum. We found that the relationship for this is much more important for dense and not dense filaments than it is for filament thickness, but they both did play a role.
Interesting.
Yep.
Marcus, I was going to ask, so the filaments that run between the galaxies that have the thicker and dense, would that just because like the overall mass of the filaments and their momentum would say overcome more of the gravity of the galaxy and stop it from falling directly in toward the core?
That's a really good question. I haven't looked very deeply into exactly how it happens yet. That could be part of it. We also know that in these filaments, especially the thicker ones, the gas will sometimes spin around the center, or will have very different patterns for how the gas moves. So it's really hard to tell just as it is, but that's definitely something I plan on looking into in the future.
So you know what happens, but you're not yet sure why it happens.
Yeah, pretty much. The why is still something we need to look into.
That just makes it more exciting.
Yep.
It's a mystery.
Yes.
Yeah, so that's our answer. A galaxy's gas angular momentum can change depending on the thickness and density of the filament it's in.
Okay, and that determines whether or not it's quenching or not quenching.
Exactly.
So you may not know the answer to this, but I know that the local group, that's the kind of three main galaxies, including the Milky Way, Andromeda, Triangulum galaxy, and the little mini galaxies around there, they're all star-forming galaxies.
Yep.
So that makes me wonder if we are actually in a thinner filament, and we have like angular momentum that allows us to have more star forming.
Yeah, perhaps. I haven't looked too much into if our galaxy here, if we're... Well, I don't know if we can tell super well if we're in a thin or thick filament here. That'd be interesting to look up.
Yeah, it's difficult for us to even count how many stars are in our own galaxy, where it's really easy to look at another galaxy and be like, oh, that's how many stars there are.
Yep.
Mm-hmm.
Alright, so that covers what I was going to talk about today. I have a quick recap here at the end. As I started with, quenching, that's when a galaxy stops forming its stars. We know that galaxies with dense cores tend to quench much faster than galaxies with less dense cores. We talked about how low gas angular momentum, where it's shooting right to the center of the galaxy, that means galaxies tend to grow dense cores and quench more quickly, whereas galaxies with high gas angular momentum means the gas is spinning around the galaxy and they tend to quench slowly.
Got it.
Yep. We saw the direction that the gas is falling in matters. If it falls in perpendicular to the disk, it's going to lose a lot of its angular momentum. And if it falls in parallel to the disk, it's going to mostly retain its angular momentum. And we also found, we know that galaxies are found along filaments in the cosmic web, and gas flows along those filaments and then falls onto the galaxies. We found that if a galaxy is in a thick, dense filament, it tends to have gas with high angular momentum, which will lead to slow quenching. And if we have a galaxy in a thin, less dense filament, it tends to have low angular momentum, which leads to quick quenching.
So for stupid people like me, The easy way maybe to say this is more gas means more stars.
Yep, that's pretty accurate.
Oh,
Yeah.
that's good to know.
Marcus, I had a question. My understanding is that we see that the central supermassive black hole in a galaxy and its level of activity can also play a role in quenching star formation in a galaxy. So, for example, if like a supermassive black hole is feeding more, it's giving off more radiation. That radiation passes through the galaxy and it might actually prevent like clouds of molecular gas from collapsing and forming like star forming regions. Is this why then? Because if there's a denser core and we have that low angular momentum gas that's falling into the center of the galaxy, is it feeding that central massive black hole, and is that what's causing some of the quenching in the galaxy?
I believe it definitely plays a role. That's actually the part of the project that I was going to start working on next. I haven't considered black holes with this data yet, but that was my next step, was to get all the data of the black holes and start comparing it to all the other things we see with the galaxies.
That sounds like a very exciting next step. I'm excited to hear the results.
Yeah, no, I'm really interested in seeing how it works out.
Yeah, definitely. So it's a theory still, and we're waiting for you to prove it.
Yep, it's in the in progress stage.
Do you think it'll be done by 10:30 when we finish streaming?
I don't think so.
Oh, okay, a little bit more work then, I guess.
Ask me in a few months, maybe.
Right. Science takes time.
Yeah, it certainly does. Right, I'm happy to answer questions if there are any.
Yeah, if there's any chat questions, fire them away, and Marcus will hang around for a little bit to answer them.
Yep.
But he won't necessarily stay with us the whole night. It's up to him. In the meantime, we're going to switch over to our camera and start looking at space. So, forgive me if I'm a little slow. This is my first time at the helm. And forgive me if my voice is a little hoarse. The thing about observatories is they're up on mountains. And when you're driving up on top of a mountain in the dark, you suddenly realize that it's probably the ideal time to belt out Disney songs at the top of your voice the whole way up the mountain, because there's no one else but you in the car. But there's a little bit of a drawback to that. Matthew, do you want to start with Saturn or the Eagle Nebula? I know Saturn's a little bit low right now. Does everyone get the list, or is it just kind of private and internal of targets?
I think, I think we keep it inside in case, so that we don't have more disappointment for the general public if we can't see all the things that we had planned on seeing tonight.
Okay.
But yeah, if you wanna pop over to Saturn just to see what it looks like now, if it doesn't look too great, we can always move on to the Eagle Nebula instead. So why don't we? I know it's been a little bit since we first opened to take a look at Saturn. Maybe it looks a little bit better now.
Got it. Okay, so if you look at our cameras on the left-hand side of the stream there, you're going to see our telescope spinning around. We're going to make it lock onto Saturn. Now, because Saturn's a bit low on the horizon, there's going to be a lot of kind of heat and interference, heat waves, I should say. So it might be a little bit blurry and wobbly and might be better for a later night target.
And Kieran, what are we actually looking at right now? What is glowing in the camera?
We were looking at Vega.
Cool.
We just picked a bright star so we could help focus the camera a little bit better.
I'm good going home. Thanks for the opportunity to do this.
Thanks for coming out, Marcus.
Yeah, no problem. Have a good night.
Have a good night. Okay, it's starting to come into focus here. Let me see if I can center on it. I'm just going to change some settings here to get a little bit brighter. As we can see, it is very
look at that.
blurry tonight.
There's Saturn right there. I'm seeing some rings.
Yes, but we can see the rings indeed. What do you think? Are you happy with that?
Oh yeah, I think that looks great. I know that my understanding is that because of the angle that we're going to be presented by Saturn in the next little while, that the rings will be so edge on that we may not be able to see them very well for a bit.
Yes, that is true. Saturn's at different times of the year and different parts of its orbit, Saturn is going to have its rings in a different orientation towards us. And in fact, Saturn's year is so long that when we rotate around the sun once, Saturn only moves a little bit across the sky from the original position it was in. It only changes about 30 days out of the 365 years worth of position across the sky.
People sometimes ask us, like, if we are looking at distant galaxies or nebulae, and some of them are like thousands of light years away or millions of light years away. So Kieran, like, if we're looking, we're able to resolve these objects that are so distant. Why is it sometimes so difficult to get a clear image of a planet that's within our own solar system?
That's a really good question. Um, the way I like to describe it is to say you should think of a cloud. From far away, a cloud looks like a very detailed and distinct object, but when you get up close to it, it's just a kind of a blurry mess. Um, Something like a distant galaxy might be much further away than Saturn, but it's so ridiculously large that a lot of fine detail is spread out across a much bigger like field of view or part of the sky. So Saturn is only, we're actually quite zoomed in. If you look at the field of view, if I zoom out here, Saturn's only taking up a tiny dot in the camera here, whereas the Andromeda galaxy would be so big it would take up the whole camera. So if you just think about how many more pixels worth of detail you're going to get on a larger object like that, that's one factor. Another factor is stars are so far away that if you're looking at an individual star, regardless of how big your telescope is, it's just going to look like a single point of light. Um, and if you had a perfect telescope with no atmosphere, it would only take up like a single pixel. And the reason it takes up more pixels than that one is because it's bleeding into nearby pixels, and there's some satellite kind of spreading out, some atmosphere spreading out the light from those pixels. I don't know if that answers your question, or if you had another point, maybe, Matthew.
Yeah, no, yeah, that's great. Thank you, Kieran. I know that when we see these images taken of planets, and people sometimes say, like, I've seen a picture of Saturn taken from a telescope, and it looks clearer than like the live view of it. And the process in which that is done is something called lucky imaging. So what we do is we will basically take a videotape, and all images of planets from the Earth are taken this way. So basically, like, a recording is taken of the planet, and in that recording, the individual frames are taken out, and then in those frames, you'll get those lucky moments where the planet is in focus rather than being distorted by the Earth's atmosphere. And if you take enough of those images and put them together, you get those nice, really clear, crisp images of a planet. Otherwise, it'll appear as they do here, which is still really cool. I mean, you can see the planet in the rings, but it looks like you're seeing it through water.
Yes, yes, indeed. Um, but those famous rings are still visible, and they weren't visible until we invented the first telescopes. I think it was Galileo who first noticed the rings, because he was the first guy to start documenting after he built his own telescope. And a lot of people are curious, like, what are those rings made out of, and how big are they? Um, they are generally made out of bits of ice and rock. It's quite small rocks for the most part, but there's some pretty large chunks in there, even moon-sized. Not our moon, smaller moons. And they're actually very, very, they stick out quite far from Saturn, but they're actually not very thick. They're about 300,000 kilometers out from the planet, but they're only about 10 meters or 30 feet thick. So they're actually extremely, extremely thin bands. And what you often see when you look at close-up pictures of Saturn is you can see a gap in between the rings, and that gap even casts a shadow on Saturn. And that gap is, we believe, caused by the seventh largest moon of Saturn, Mima. Saturn has quite a few moons, and Mima is close enough to the rings that it actually creates a disruption, and that ring gap, called the Cassini division, which is the largest gap between Saturn's rings A and B, is caused by this moon's gravitational effects on the rings, as far as we know. So yeah, it's kind of interesting to see an object so far away from the actual rings itself, just with the effects of gravity, kind of like a big magnet sucking everything to one side and changing the density of the rings.
There's a question in the chat that people have said that they might be seeing dots in the image that are the moons of Saturn. And so I don't know if we jack the brightness up there a little bit, Kieran, if it's actually possible to see some of the moons. I think Titan usually has a very high reflectivity because of its atmosphere. It might be visible
I think we can, yeah. If I really jack the brightness up like that, You can see on the left there a dot. Any guesses for which moon that is? It could be Titan. Titan being the,
There it is.
yeah, second largest moon we have in the solar system.
Yeah, I think that is likely it. I remember there was a Twitter feed where if you punched in, I think it was like Titan moon position or Jupiter moon position, it would show where the moons were relative, like as characters relative to the planet.
That's pretty useful, yeah. And Titan is an interesting moon. It has lakes of methane, so it's cold enough that the methane has gone from a gas phase into a liquid phase. And it's one of the two places on one of the two most promising places to look for life in our solar system. The other one being another one of the moons of Saturn called Enceladus. Enceladus actually has liquid oceans, as in water, and even when they sent the space probe, I think it was the Cassini space probe past it, it took pictures of jets of water shooting out of the surface of that moon. And that's why they want to send a probe into Enceladus, actually underground potentially, to probe the internal environment and see if it's got conditions that are viable for life. It would be a good place to look for potential life outside of Earth. The only problem is we have to be conscientious, just like Starfleet Academy from Star Trek, and we're not supposed to contaminate any other life. So sending a probe made on Earth to another place and then having it go in there could potentially contaminate or harm the life there. So it's something the scientists take very seriously when they're planning these sorts of missions.
Yeah, that's why we burned the Cassini probe up in the atmosphere, right? Because we don't want to contaminate at all. There was a question here in the chat, good one. How far are Saturn's moons from Saturn compared to the distance of our moon from us? So Saturn's moons can orbit quite far away. So one of the most distant of Saturn's moons is 3 million kilometers from the surface of Saturn versus about, on average, I'd say close to like 350 to 400,000 kilometers with our moon. Titan is itself 1.5 million kilometers from the surface of Saturn, so quite farther, a lot farther away, greater radius, orbiting radius than our moon.
Mm-hmm. And the moons play a big role in whether or not planets like Saturn actually have rings. Titan's far enough that it doesn't disrupt the rings too much. Our moon's actually relatively close to us. It's about 390,000 kilometers away. And that is one of the leading theories why planets like Jupiter, which are, bigger than Saturn and have more gravity, don't have visible rings. Is because Jupiter has so many big moons close to it that they probably scooped up all the matter that would have formed rings long ago. And even though Earth is a pretty small planet compared to gas giants like Saturn, it's actually got the 5th largest moon in the solar system, Luna, our moon. And because it's so ridiculously large and close compared to the size of our planet, if we had planetary rings, there's a good chance the moon would disrupt the orbits of them. If you think of that gap between rings A and B on Saturn caused by a smaller moon just kind of near the rings, imagine our large moon making a gap in the entire ring until the whole ring's gone. Basically, things would either end up on the moon or their orbit would get disrupted and they'd fly off into space or crash into the Earth. And so that's one of the leading theories why there's only 2 planets that we can see rings visibly. Can you guess what the second one is, Matthew?
Is it the one that's like the butt end of every joke in the solar system?
I see. You're beating everyone in chat to the jokes about Uranus. Yes, indeed. Uranus actually has some really dark rings that we didn't. I don't remember when we first discovered them, but it was quite a while before we saw them because they're not visible through conventional telescopes like Saturn's rings here are. So why don't we move over to something a bit less blurry than this?
Mm-hmm. So the rings are also talking about the gas giants and their various moons. We have some future missions going to Jupiter's moons. One of them is called JUICE. It's an acronym that I'm going to butcher, but it's like the Jupiter Icy Moons Exploration Mission. But basically, we're going to be looking at these moons more closely. Another mission, the Europa Clipper, coming up As we know now that a lot of these moons have subsurface oceans, they might be places where we find life. I'm excited about those.
That's just my old image of Vega I have to clear out of the memory. So what we're going to do now is we're going to stack images on top of us. So what we're looking at now is much further away in space, and it's much dimmer than Saturn. It's difficult to see without what we're doing, which is called image stacking. So basically we're going to take a lot of different photographs and we're going to stack them on top of each other, and we're going to add all of their light together. As well as doing that, we're also going to take a longer exposure. So it takes about 20 seconds. I just reset it now. So it's going to take about 20 seconds. The shutter is going to be open. We're going to take a long exposure, and then in another 20 seconds, we're going to take a second exposure and overlay that on top. And as these add up, we're going to get a clearer and clearer image of what we're looking at, which is the Eagle Nebula.
It's one of my favorites, and one of the main reasons is that the Eagle Nebula was the first space poster I ever had in my house. So there you go. So in my room, the Eagle Nebula, because that was a big deal. It was the first clear photo that the Hubble Space Telescope took. So for those of you who don't know, when the Hubble Space Telescope went up, it had a problem in that its lens or its mirror was ground to the wrong prescription. In that it actually was to the prescription that was ordered. So it wasn't a manufacturing error, it was an order error. And when the telescope went up, it was taking blurry images, and it needed corrective lens to be attached to it. So I'm in good company since I wear corrective lenses as well. I'm also nearsighted like the Hubble Space Telescope. But the first clear image that it took was of the Eagle Nebula, specifically the formation that you can see now being resolved here on the left, the pillars of creation. Now normally we see this image 90 degrees rotated, counterclockwise. You've probably seen it in posters, but the angle that we're looking at it right now through the telescope, you're seeing those pillars here of the Eagle Nebula.
I notice it's very red looking. I think that is probably due to hydrogen, which tends to be picked up in red wavelengths of light. What can you tell me about the pillars of creation?
Yeah, so the pillars of creation themselves are one of the features of an entire larger nebula known as the Eagle Nebula. The eagle itself looks like it's kind of like swooping down and picking up the pillars as if like it's snatching up worms kind of in its beak. We're looking at this about 6,000 light years distant. So whereas if you compare that to Saturn, which we were just looking at, Saturn is like in light minutes of time away from Earth. So this is light years away from Earth. The pillars themselves are illuminated pillars of ionized gas. So this is basically, as you were saying, Kieran, hydrogen gas. And hydrogen gas, when it tends to be lit up from the energy of stars, tends to glow this kind of like a reddish color. And so it's kind of like when you put energy through like a fluorescent light tube and that gas inside glows. That's basically what we're seeing here. And we call those emission nebula. So there is light being emitted by the gas, and the gas itself is being energized by the light of new forming stars, because this is one of the places in our own galaxy where stars are being born inside of these pillars, hence being called the pillars of creation.
Oh, I never knew that about the name. That's very inventive. Fun fact about nebula like this is I don't know how many of you have seen Guardians of the Galaxy or any of the Marvel movies. They were pretty popular up until recently, and you'll notice there's a lot of colors when they're flying around their ships in space in a lot of these works of science fiction, because they like to pick nebula and then fly through them and be like, oh, everything's green and red and blue. But again, if I go back to that analogy about clouds I made earlier, from a distance, this Eagle Nebula looks very resolved and distinct. You can see all sorts of features. But if you are actually in it, just like when you walk into a cloud, all you see is fog. Well, imagine a cloud that's spread out over light years. Now you're basically not going to see the cloud at all. It's like a water droplet here and then another one on the other side of the hill, kind of distance. So this is a long exposure collecting a lot of light with a camera that's much more sensitive than our eyes. As beautiful as that is from far away, if you were actually inside the nebula, you might not even notice the gas around you. It would be so dispersed, and it probably wouldn't even look colorful to you. It would just look like black space in a lot of these places.
Don't spoil it for me, Kieran. I want the colorful space nebula from Guardians of the Galaxy.
Well, funny that you mentioned that, because our next target probably would actually look in fact, guaranteed would look very colorful if you were relatively close to it.
One last thing before we move on. There is a speculation as to whether or not the structure of the pillars still exist, because there was some indications that there may have been supernovae that had occurred within the clouds. This cluster is pretty young, relatively speaking. It's only 1 to 2 million years old. So and there's about 8,000 stars being born in it. But in a cluster like this, the largest of those stars, these giant, we call them type O blue giants, only live a few million years. And so one of the largest inside of the nebula is 80 times the mass of our sun. So and 1,000,000 times the luminosity. So imagine a star 1,000,000 times brighter. So even though these clusters are still giving birth to stars, some of the largest stars are already dying. And if they were to explode, it would disrupt the structure of the pillars. But recent observation seems to suggest that they're likely still there. So we're probably, if you could transport yourself right now to the pillars of creation, although they wouldn't be as colorful as you pointed out, they are probably still around.
But that does bring the question, if it exploded today or was disrupted right now, why would we not notice it right away?
And that's a great question. And part of that is because when we are seeing objects like this, because they are so far away, we are experiencing something called the look back time. So we are literally looking at this object as it appeared 6,000 years ago, before even the pyramids were constructed on our planet. So the farther we look back in space, we are looking backward in time. Even if you look at the moon, it's 1 second in the past, the sun 8 minutes. So every time you're looking up, you are literally looking at the universe's memories.
And that's because if it's 6,000 light years away, it took 6,000 years for the light to reach our eyes.
Absolutely.
Fantastic. So if I want to find out what my dad was doing in 1985, I just have to travel, let me guess, like a certain number of light decades away, and then point a really big telescope back at him and go, "Ha! Caught ya!"
Yeah, you'd have to kind of do that instantly, because you'd have to get ahead of the light that is already traveling away from Earth. But if you had, like, a TARDIS, like Doctor Who does, and you could travel instantly through space, you could technically look back in time. If you could say, maybe you could leap yourself 150 million years, light years away from Earth instantly, you could catch the light that had left from Earth, and you could be looking at the dinosaurs wandering around on our planet.
Give Marcus a couple more months. I'm sure he'll figure it out.
That's right. Go, Marcus. That's your next mission.
Okay, ready to switch targets?
All right, let's do it. The next one up, I believe we're switching to the Ring Nebula.
Indeed. So let me just clear the current image and wait for it to take a new one. So the Ring Nebula is also a nebula, much like the Eagle Nebula, but it is a different kind of nebula. It has formed for a different reason. But what does it have in common that makes it a nebula? Well, it's made out of gas. So I am going to adjust some levels here. Oh wow, it's coming really beautiful tonight, I have to say. So again, just like Matthew was saying, this is made out of ionized gas, and to clarify, ionized gas is much like a neon light bulb, which has neon gas inside of it. They run electricity through it, the gas gets excited and ionized, and it starts to glow in the frequency that neon gives off. Well, much in a similar way, the Eagle Nebula gets excited by the energy from the stars within it, and it starts to glow in the colors of the gases inside the Eagle Nebula, which is primarily hydrogen, which glows in that red color that we could see. Well, as you can see, this is a very colorful and very structured nebula, and it is much smaller, much smaller than the Eagle Nebula. So this is what we call a planetary nebula. It's in the constellation Lyra, and it's about 2,500 light years away. And when they first started discovering nebulae like these, when telescopes kind of got good enough that they could see them, they were really not sure what they were. They were still discovering the planets at the time. And because there were these round, kind of blurry stars that weren't quite as focused as stars, they kind of, in shorthand, were like, well, it kind of looks like a planet. In fact, in 1779, the French astronomer Antoine Darguier de Pellepoix, I have no idea if I'm saying that correctly, he wrote down, it's very dim but perfectly outlined. It is as large as Jupiter and resembles a fading planet. and that name kind of stuck. William Herschel called it a planetary nebula because it looked kind of like a planet. And the word planet comes from the ancient Greek word, which means, I think it was planon, and that meant wanderer. Because when you looked at the planets, they looked like stars, but they wandered across the sky in ways that stars do not, which are all fixed to their own rotation with each other. And so it was confused with things like planets, but it actually has nothing else to do with the planet. It is much larger than the planet. In fact, could you perhaps tell us what exactly this thing is, Matthew?
Yeah, I mean, this is we're looking at our future here. This is what our star will probably look like in 4 billion years from now. So nothing we need to write down on the calendar or be worried about necessarily. But this is a star that has died, and stars like our sun, eventually, once they run out of fuel, they enter a new phase in their life where they become something called a red giant. And I think one of the better descriptions I've heard of this is like if you've ever gone camping and roasted a marshmallow. It's like if you roasted the marshmallow, it kind of swells up into a big pile of goo, and if you let it keep going, it'll eventually just kind of melt away. And that's essentially what's happening. This is like a star that is puffed up like a marshmallow, and eventually its outer layers are shed off into space. And the cloud itself is expanding, so the gases here from the Ring Nebula, it looks like it's frozen in space because we're looking at it from far away, but the outer edges of it are actually receding from the star at about 30 kilometers per second. And the outer areas are going to have the lightest of the gases, and which in this case are hydrogen. And like Kieran mentioned in the previous, when we were looking at the Eagle Nebula, we can see that reddish color. And so this is hydrogen again that is glowing here because it's the lightest of the gases. It's going to travel faster away than the others, and so you get this natural gradation from the lightest elements to heavier. The bluish and the kind of green on the inside is going to be oxygen that we're seeing shedding away from the inside. And at the very center, and we can actually make it out in this picture, at the very center of the nebula is something called a white dwarf, and it essentially is the burned out central mass of the star, the core of the sun, now an ember drifting through the cosmos.
Yeah, and it's quite interesting. Like, even though we say this is the end of the life of the star, that white dwarf will actually last an incredibly long time, probably longer than any star has existed so far, according to our calculations. From what we understand, no white dwarf that has been created has yet burned out from that phase, basically. So they last an incredibly, incredibly long time, and this is kind of the future fate of our sun. Basically, like he said, it's going to expand to red giant, and then it's going to destabilize as it runs out of its primary fuels, and then it's going to expel its outer layers. Now, this is not a nova or a supernova. It's not exploding in a big kind of reaction. You need to be about 8 times more massive than our sun to have a reaction like that. And it won't collapse into a black hole either. There's not enough mass to suck everything back into a black hole. So instead it's going to expand and then just continue to expand until the outer layers shed off and the kind of neutrons and heavy subatomic particles remain in the center, and the lighter gases expand out. But this is actually a very good process for us, because there are certain elements that are only fused or formed inside of stars. And when a star has a sort of death like this, those elements that were created can now expand out and go out into the galaxy. And so even some of the elements that we require to live, like iron and gold and things like that, are created either in supernova explosions, or perhaps carbon, oxygen, some of the lighter elements are created just inside stars' cores naturally. And if stars didn't go through this death process and shed their outer layers or go supernova, we wouldn't have access to those heavy elements. So if you think back to the early universe, at that time, everything was basically just hydrogen and helium. And it wasn't until stars went through their entire millions-year-long life cycles, some went nova, some went red giant, and all of the heavier, denser elements than hydrogen and helium that they had created in their cores or during those supernova explosions were dispersed into the galaxy, and now those could come into planets like Earth and give us things like iron tools or iron in our hemoglobin blood, so carbon to base life off. These things require the death of stars to exist. So that's kind of an interesting fact. And
full circle.
Yeah, exactly. And this is probably only about 2,000 years old. In the time of the pyramids, they would not have been able to see this. most likely because these don't last very long. It'll only be several thousand years, and then the elements will have dispersed enough that they'll no longer be glowing and as visible. So it's a nice time that we get to see these very specific planetary nebula that are in our sky, and thousands and thousands of years time in the future, the pillars of creation will look different, and we'll have different planetary nebula from different stars that have gone through this sort of death process, as we call it.
Kieran, there's a question here in the chat that asks whether or not the gases expelled from a white dwarf or as a red giant into a planetary nebula, could it recombine around the same dwarf as a new protoplanetary disk? So could new planets form around an object like this?
That's a really good question. So it all depends on velocity, really. And I'm going to probably guess not. And the reason I would guess not, and I'm not an expert in this field at all, is just because of the temperature of these gases. They're very hot. So if you imagine Earth sitting near the sun, and the sun starts to shed its outer layers, Earth's going to get vaporized. It's basically going to turn into gas itself. And anything that's light enough, like gas particles, that's not like heavy rocks or whatever, is going to feel something called radiation pressure. So basically, when you shine a laser on something, it actually puts a tiny amount of pressure on that object. So if you were to put something in space and shine a laser on it, eventually that thing would start to gain momentum and move away from the laser because it's getting pushed. And imagine the extreme heat and energy output by a star, even a small star like a white dwarf. And these tiny, tiny ultralight gas particles, they are so light that only the smallest amount of radiation pressure, this light and this energy and these kind of rays coming off the star, are going to start to push that gas away. So it's kind of forced by this radiation pressure to be pushed away from the star. And so if there is some kind of maybe heavy matter coming in from another direction or something, it is possible, especially if the white dwarf has already expelled all this gas and maybe it's just sitting there. Yeah, I mean, potentially, maybe if it had an interaction with another cloud of gas or something. But as for the material that came from the star itself, I've never heard of anything like that. I'm not going to claim that I know because I'm not an expert in this field. But from what I do know is pretty much everything caught in that expansion is going to be vaporized, turn into light gas, and then be pushed away by this radiation pressure. And
yeah, I think that makes sense. I'm thinking too about the expansion rate of the gases, like around 30 kilometers per second. Like that's close to the escape velocity of our own solar system. And if a lot of the mass has been spread out from a solar system like this, I would imagine that material would just continue on a trajectory away from the whole solar system.
Yeah, but that being said, on a cosmic scale, 30 kilometers per second is not that fast. So if something from outside this little white dwarf solar system came in from another direction, it being captured by the white dwarf is not out of the question. I would say,
yeah.
because we believe there are rogue planets that don't have stars. If it could fly along and get captured by the gravity of the white dwarf and end up orbiting it, some kind of weird dead star with a dead planet around it, would be a great setting for a science fiction novel.
If I'm right, one of the first ever confirmed exoplanets was orbiting a neutron star, and I don't know if we ever found out entirely how it got there.
Yeah, it also could be that it was far enough away in its orbit, because remember, most of the exoplanets we pick up are very large and very far away from the star. It's easier to detect them that way. If it was far enough away from the orbit, perhaps it was not vaporized by the expansion of the outer layers. Perhaps the outer layers were diffuse enough by the time they reached it that, yeah, maybe all the gas got rid of the atmosphere, but the planet, or damaged it or something, but the planet didn't necessarily get wiped out. Yeah.
Cool.
Mm-hmm. And that's kind of an interesting thing. Like if radiation pressure is pushing this gas away, same with the Eagle Nebula and the pillars of creation that Matt was talking about. Those stars being born, even before they become white dwarfs, or if they're never destined to become white dwarfs, they have radiation pressure. They are putting out a lot of light, and that's actually pushing the gas away. And this is going to cause, even without the supernova explosions inside the Eagle Nebula, it's going to cause constant changing and shifting of the Eagle Nebula and how it looks. And eventually, over time, between 60 to 90% of the gas in the nebula will probably be pushed out completely, and you'll just end up with the stars that are left over and not that much gas. And that actually links back to what Marcus was saying earlier, is this actually happens to entire galaxies. Spiral galaxies have a lot of gas and dust in them and a lot of star formation. The elliptical galaxies, partially due to things like radiation pressure, have no gas left in them to form new stars. And so they've got just old stars, red stars, none of the new young blue stars, and they're what we call red and dead galaxies. So it
Yeah,
kind of affects
and in the
everything.
interim, until the structure is completely diffused, some of those supernova shock waves actually trigger the collapse of other dust clouds, which then lead to more star formation. So it's this amazing cycle of like birth, life, death, more life, kind of over and over again until you basically run out of fuel.
Yeah, exactly. And even a red and dead galaxy, we'll get to this later if we have time. There is ways that it can be reignited with life again, but I'll leave that as a little secret for later. In the meantime, we've got I believe one of your favorite nebula is the Maya Nebula. I'm actually quite excited about this one because I didn't know anything about it until tonight. So let's move over to that one.
Yeah, I think this is a little bit of an experiment because I don't know if we've ever tried the Maya Nebula on this camera before, so I'm hoping it will actually show up. As we're moving, another question here about if this is a spherical object, the nebula, how can we see toward the center? And I think, Alexander, if I'm right on this, it's because the expansion of planetary nebula like this are not exactly symmetrical. So sometimes if you could actually rotate the object around, it would be lobed out and kind of towards sides in different directions. So we might actually be looking down inside of like one of those sort of donut-y shaped type lobes to get more of a view toward the middle. I don't know if that's 100% accurate, but I think that might be what. Kieran,
I
do you
feel
have
like
any input on that?
yeah. So one thing, I think the Maya Nebula might be a little bit too low on the horizon right now, so we might have to switch to another target.
Okay, no problem.
We
Yeah,
might be able to have to do it later tonight.
Okay, cool. Yeah, I was wondering about that too because it is in Pleiades, and Pleiades is still pretty low in the horizon, so maybe we can check it out later. Do you want to switch over to the wild duck cluster then? In the
Yeah,
meantime?
I'll do that in the meantime. So
Alright,
just
sick.
remind me the question. Oh yeah, so that is a really good question. That is part of the answer, definitely. A lot of these are not perfectly spherical. The first nebula they found, I believe, was the dumbbell nebula, and it's shaped, like the dumbbells you lift to lift weights. It's got like a lobe on each side. But it's not just that. If you think of a halo around a light bulb, it does tend to look brighter on the sides than in the middle because the bright light from the middle is going to pierce through that red sphere on the outside and overwhelm it. So when you're looking at the left and right, like this red circle around it, you're looking only through red light. When you're looking at the middle of the nebula, you're also seeing the red light, but the blue light shining from the center and the white dwarf is so much brighter that it overwhelms the red light, and you're going to see that blue kind of more starkly. So a lot of these things are, they're still pretty spherical, but it's definitely not like, Star Wars or any science fiction where you see an explosion in space and there's a shock wave that comes out in a perfectly parallel line. That's not really realistic. Explosions in space tend to be spherical. So it's a really good question. Yeah, absolutely. I hope I answered that well.
Yeah, totally. In fact, I remember watching. Now that you're talking about Star Wars, I watched some of the ways in which they do make spherical explosions or low, like zero gravity, I guess, explosions in science fiction films. So what they did is they would film the object from underneath, so they suspend it above the camera and explode it so that it radiates out in all directions. Although I do love the classic ring shockwave when the Death Star explodes in New York.
Yes, there is something fun about watching Obi-Wan dodging that. Okay, I thought I switched to the wild duck, but maybe there was an error here. Let's try this again.
We might be, maybe, are we in a cloud? Are we starting to get some clouds?
No, it went back to the ring, even though I asked it to do the wild duck. Don't ask me what's going on. Okay, I've switched over, and I'm gonna clear the stack, and we will see. I think I gotta clear one more image, and then we'll wait 20 seconds, and we should see the wild duck cluster in a moment. Now it is currently at 29 degrees altitude, so it should be high enough. Yes. Okay, wow. That is bright. Let me adjust this. Oop. Doop, doop. So, what we are looking at here is what you would call an open cluster. And an open cluster is a bunch of stars with similar properties that formed at the same time. And you'll notice they're very dense. If you're thinking of our field of view that we were looking at Jupiter before, we're seeing all these stars in the same field of view, but at a distance of about 22,000 light years away, as opposed to 8 light minutes. So if you think about how many minutes are in a year, times that by 22,000, that is much further away. And look at how many stars there are all close together. This is much denser, I would say, than the local region where our sun is and our closest stars to us. Now, an open cluster is a bunch of stars that form together, and this links back to the Eagle Nebula we were talking about earlier and radiation pressure. What most likely happened is there was something what we call a giant molecular cloud. No prize for guessing what a giant molecular cloud is. It's a large cloud of molecules. Yeah, very creative name. And basically, it's full of gas and dust, and a lot of this gas has gravity, and it all sucks together and starts to form stars. And then what happens is when you reach a certain critical mass, between 10 to 40% of that gas has become stars. There's enough radiation pressure from all the stars giving off light to push all the rest of the gas away. And there are probably some of the largest stars have gone supernova, which has also kind of excited the gas and pushed it away with even more energy. And you're going to get something like this. It's the leftover after the gas has gone away. So if you took the Eagle Nebula, took a big sieve and scooped all the gas away, you would get something like this. And they called it the wild dust cluster because sometimes when you look through a telescope, the brighter stars are kind of shaped in a triangular formation, like a bunch of ducks flying overhead. And that's how you can tell it was not a Canadian who named this cluster, because we definitely would have called it the wild geese cluster, because, you know, our national animal and most vicious predator is the Canadian goose. And
So, how long would it be? So, in a cluster like this, Kieran, so are they
Yeah.
going to stay in this state? What would be the fate of a cluster like this in the distant future?
Yeah, that's a good question. So, well, how do we determine that? I mean, we have to look at other clusters, and we found more than 1,000 in our galaxy. There's a lot of gas and dust obscuring our galaxy. We estimate there's many, many more than what we have found so far. And we even estimate that our sun started in a similar situation like this. So why aren't we in a densely packed region full of similar stars? Well, here's the interesting thing we can do. If we look at all these stars, because they formed in the same cloud, they formed from the same material, which means they have the same chemical makeup. And as Matt was saying earlier with seeing hydrogen glowing red, every element has its own kind of spectrum that it glows in. So we can point our telescopes at stars, split the light into a spectrum, and determine what elements are in them. And we noticed that these clusters, all the stars are made out of the same stuff because they were all created in the same giant cloud, which had similar properties. So we look at the stars around us and we go, oh, there must be stars in the kind of neighborhood of our sun that have similar properties to the sun or almost identical makeups. And so that's exactly what we did. And we found a couple of stars, I think what we call solar siblings. In 2014, we found one. It's just got a catalog name like HD162826. And we have found a second sibling in 2018. So these are stars that are not super close to us, but they're close enough to be potentially from the same molecular cloud. And what happened with these is they likely got spread apart from the sun at some point. So how did that happen? Well, as we observe these clusters and we can see different clusters in different stages of their lives, we can determine that because they're relatively small, only like a couple of dozen stars to several hundred, they don't actually have that much structural integrity compared to the entire galaxy, which is on a really large scale. And because they last so long, they could go around our galaxy like 20 times since they were formed. And in that time, in that journey, they are interacting with gravity from all sorts of things, other stars, the big black hole in the center of our gravity, all the nearby matter. And so they actually kind of get slowly spread apart, and they kind of disperse into the galaxy. So that's kind of the eventual fate that's most likely for something like this. And that is what we think happened when we started to find these sibling stars nearby. We think, okay, these are remnants probably from the molecular cloud that our sun formed in, because they have the same properties. And they've been spread out by, I mean, our sun, I think, has gone around the galaxy 20 times. I didn't just randomly choose that number since it was born. So that's kind of let the cluster get torn apart. But that does actually segue to an interesting thing. Is soon we're going to look at a much bigger kind of cluster that has managed to maintain its integrity for a very long time due to its size. But before I switch to that, I do have one other fun fact. Thanks to the JWST, the James Webb Space Telescope, and its massive mirror and its super sensitive camera, we've been able to detect exoplanets in other clusters. We even found something called a hot Jupiter in the Beehive cluster, which is basically, as long as our data is correct, the studies came out quite recently, what we call a rogue planet. It's enough matter congregated due to gravity to almost form a star, but it wasn't quite hot enough to be classified as a star. So it's like a really big planet like Saturn or Jupiter, even bigger, that glows in the infrared spectrum because it's so hot. And the JWST telescope detects things in the infrared spectrum, so they were able to detect these rogue planets. And it looks like they were often orbiting each other, but they didn't actually have a star. So it's really good evidence that planets can form without stars, and it would make sense from our understanding of physics that they could. And now we've got what looked like confirmed rogue planets. So it's very likely that, yeah, they exist. And when we think back to Saturn, the interesting thing about Saturn is it actually emits about 2.5 times more heat than it takes in from the sun. And that kind of gives you an idea of how stars start to form. As planets get bigger and bigger, they start to generate their own heat. And big planets like Jupiter and Saturn actually give off more heat than they receive. And if you kept adding mass to that, it would eventually become what we call a hot Jupiter, giving off so much heat that you can detect it from far away with the JWST. And if you kept adding mass to that, it would get bigger and become what we call a brown dwarf, which is like something between a gas giant and a star. And if you added enough mass, it would eventually get hot enough and enough pressure to ignite a fusion reaction, like in our nuclear fusion reactions. If we could get a nice nuclear fusion reactor to work long term, something as big as a star would actually accomplish that. And that's how stars kind of ignite and turn into stars, when they start having fusion instead of just generating heat due to pressure and gravity and friction and things like that.
So in 2010, the movie slash book, the aliens that are there, they want Europa as another home in our own solar system. So they collapse Jupiter down so that it ignites and becomes a second star in our own solar system. But like, what order of mass are we talking about that we'd have to actually add to Jupiter or a gas planet for it to become massive enough to actually burn and become a sun?
That's a really good question. So I think what the aliens did is they didn't have to add mass. They just had to squish everything together. And if you add enough
They had
pressure,
space powers. They did it with space magic.
And that's why we think we'd be able to create fusion on Earth. We don't need all the gravity of a star. We just need the conditions that the gravity of a star generates. That is enough pressure to squish everything together so tight that molecules start to fuse together and you get fusion. You need a lot of heat and a lot of pressure. So technically, if you could squish Jupiter down, theoretically, if you had some way to do that, you could ignite fusion, and it would be like a tiny star. What the exact order of how much mass you need for a star to ignite fusion is, I'm not sure, but it is much, much larger than Jupiter. There's planets out there that are multiple times bigger than Jupiter that have not ignited into stars. So don't worry, Jupiter's not going to go star anytime soon.
Right, yeah, and I think you get this interesting equilibrium that happens, that even though you're adding, say if you have objects like some of the smallest stars, they are far more massive than Jupiter, but because of the increase in gravity and density, they actually aren't much larger. So they're around the same size as like a gas giant planet in our solar system, but they are in fact, like a red dwarf star.
Hmm. There have been some studies done, according to certain encyclopedias and authors, uh, and they think that it's something like 1/10 of the sun's mass would be all you need to actually start igniting, fission and fusion reactions. So, yeah, that the sun is many, many times bigger uh, than Jupiter, and it's not even close to 1/10 of the sun's mass. So, a long way off. So, I think our next segue would be to the natural follow-up, a much bigger cluster called M13, the Hercules cluster.
This is one of my favorites.
So again, we are going to move the telescope. You should see it spinning. And our dome is going to slowly catch up. And once the dome's caught up and we can look out of it, I'm going to clear the stacks.
So Kieran, while you're doing this, you've been mentioning a stack and clearing a stack. What does that mean? What are we doing when we're stacking images?
Yeah, I think I went over it at the beginning, but I will refresh. Basically, Saturn's nice and bright. We were only opening the shutter for 5 milliseconds, so that's 5 thousandths of a second, and we were getting that nice bright image. What we're doing here is we need a lot more light because these objects are much fainter. So we're exposing for 20 seconds at a time, and every time we take another 20-second exposure, we overlay it on top and take the average of the two exposures to get more detail and more light out of our image. So there's pros and cons to both long exposures and to stacking multiple images. If you only take a long exposure and don't stack images, you get so much noise, kind of like electronic interference and from heat, etc., in your image that you don't get a nice clear image. So you want to combine both techniques. You want to get an average of many images, and you want to get a long enough exposure to have enough light. So if you look at this histogram at the bottom, I hope you guys can see it. What I'm trying to do is line up these colors, these color lines here, and that's just to give us more of an idea of kind of the three frequencies, because again, it's a color camera. It's got green, red, and blue pixels, and if I line those up, it's going to show you a color that's more accurate to what we naturally see, hopefully. So these images that we're looking at, including that really bright Ring Nebula, they aren't just like magically enhanced color images. They are actually the real colors of these objects. And looking at M13, I notice it has a lot of different colors in it, which is quite interesting. So what are we looking at here, Matthew?
So this is a globular cluster. So in contrast to the previous one we were looking at, which is an open cluster, this is mainly like, it is compact, but it was basically new stars that are being born. This is the opposite. This is a cluster of very, very old stars on the order of billions and billions of years, probably like around the time that the galaxy was forming. Now, we're not entirely sure how these clusters are created, but one possibility is that they are formed when galaxies collide with each other. So opposite of kind of what Marcus was talking about at the beginning of the show, when galaxies' star formation is quenched, when galaxies collide with each other, they can go through rapid phases of intense star formation. We call them starburst galaxies. And that can sometimes happen when we think the galaxies collide. All that raw material that can form new stars gets churned up, and you have these giant knots of star formation that occur, thousands and thousands and thousands of stars. And a cluster like this could be over 100,000 stars. And because they are so densely packed together, and because there are so many stars creating all this gravity, they never separate from each other. So unlike the previous cluster that eventually will disperse into the galaxy, this one kind of stays bound together. And there's a number of these globular clusters, so-called, in our galaxy. So there's probably over 100, I think there's around 150 in our galaxy that we've seen so far. And they tend to orbit around the center bulge of our galaxy, and they're quite far away. So this one is 22,000 light years away, and it looks really cool in the camera, but it also looks really cool in the eyepiece. So this is one of those things in the eyepiece that we tend to want to show to people with your own eye. That you can come in and see it, and it looks almost like a cloud of fireflies. Now, you mentioned colors, Kieran, and one of the things that you can see here now that you've adjusted the color is that you might notice that there are some blue stars in here. And this is actually a little bit of a mystery because blue stars tend to burn out within a few million years, and yet this cluster is billions of years old. They're called blue stragglers. And what we think actually happens is that this is one of the few places in the galaxy where stars will often collide with each other because the cluster is so densely packed. And when stars collide, it looks like maybe they can almost like refresh themselves and create a new blue star. And we call these blue stragglers that might be formed by the collisions of these other stars. This is one of the brightest ones in the northern hemisphere that can be seen. There is one brighter in the southern hemisphere called Omega Centauri. That cluster might actually be the center of like a merged dwarf galaxy with our galaxy, so it's sort of like the center of another smaller galaxy that was consumed. And this one's really big. Like if you can see it, the whole thing with the naked eye in the sky, it is almost the same size as the moon. So it's quite large in our sky, where of course we have to usually use a telescope to see most of it, and our skies are too bright in order to see it otherwise. But it is really large, and it is one of the few places in our galaxy that we have sent a message to. We don't do a lot of intentional messaging in space, but there was a message from the now defunct and collapsed Arecibo array, but we sent a message to this star cluster that's known as the Arecibo message. Contained a bunch of interesting things like shapes of humans and the number of like representation of DNA helix and like our solar system and some other stuff like that. Of course, it won't get there for tens of thousands of years, and if anyone's there to send a message back, we're not going to get it for a while.
Yeah, it's definitely one of my favorite things to look at, and you can actually see it with a pair of binoculars on a dark night. It's large enough and bright enough. A good pair of binoculars or a small telescope. It's quite interesting what you're talking about, the blue stragglers. I did a course on nucleosynthesis, one of my favorite and most interesting courses, and there was a big section in that course that was teaching about the suns and the stars. And one of the reasons why these stars change color is because they kind of run out of their primary fuels. So when they're blue and hot, they're burning primary hydrogen and helium, but eventually they burn out of that stuff. And it's not burning like a fire, like you light a torch and it just, combusts right away. When we say burn, we're actually talking about nuclear reactions like fusion and fission. And these are much slower reactions. A lot of hydrogen can sit there, and only a small percentage of it has a small chance at any given time to actually react in this way, often using quantum tunneling and really interesting processes like that. The interesting thing about these stars is they still have the helium when they turn red, even though they stop burning it. They have a little bit left, but the conditions, the pressure, the gravity, the heat is not correct for that helium to necessarily all be burning at the correct rate. So if another star comes along and collides, it's now going to change the gravity and the dimensions of the star and the temperature, and it might reignite those helium fission processes, which would make the blue light start being emitted again. So again, I'm not an expert in this, but that was what I understood from that course I took.
Yeah, that sounds very similar to even like the way that hydrogen reaches the core of different mass size stars, right? So like, when we were talking about smaller stars like red dwarfs, they're very convective, so that hydrogen has a chance to constantly be refreshed into the core and circulates through the entire star. Where if you get like a really big, massive blue star, despite all their mass and all that hydrogen that's there, because they're emitting so much energy from the core, a lot of the hydrogen gets pushed to like the outer layers of the star and isn't able to actually get into the core, and so they're not as efficient. They don't burn as efficiently.
Exactly.
So it sounds like what you're saying is that it's like when the stars merge, they remix, and all that extra fuel is able to get into the center of what becomes kind of like a new star.
I'm not an expert in that, but I do know that it's also just the conditions change too. So with different temperatures and pressures, you're going to have conditions that are more viable for hydrogen and helium to fuse into heavier elements. And I remember the way my professor explained it, a wonderful Polish gentleman, he mentioned to us that stars have layers, and even our sun, it's not kind of uniform from one end to the other, and different types of reactions are happening in different layers. So he compared it to us. He said stars are like onions, and I leapt out of my chair and pointed a finger at the board and said, "Stars are like ogres!" And he just kind of stared at me blankly, but at least I got a laugh out of the class.
I think one of the things that helps us when we look at objects like this in space is to find like a comparative analogy. I think of how often that we do in science communication, we're always looking for something to help us understand otherwise like complex things. And yeah, stars very much are like these layered objects out there in space, and those layers will contain those heavier elements. Like you talked about earlier, that if it weren't for the explosion of the star, those layers are not going to get out into space and reach us and then become a part of our own bodies.
Absolutely. And we were looking at an open cluster earlier. That's a small group of stars that formed in a molecular cloud. They don't have the strength to hold together when they're rotating around the galaxy many times. Then Matthew was showing us M13, Hercules cluster now. It's much bigger, many, many more stars, and it has enough dense gravity to keep the structure together even as it rotates around the galaxy. But I want to go bigger. Like, this is almost a proto-galaxy here. It's like a mini galaxy with a lot of stars that have similar properties. And I want to note, we sent a signal to this cluster before we studied its metallicity. And a metallicity study is basically detecting the heavier elements in something like this. Astronomers call it metallicity, but that means anything basically that's heavier than hydrogen or helium. So even oxygen is a metal from an astronomer's perspective. And they discovered that the metallicity of these stars, because they have similar properties, are actually very low. And things like iron are like 4% as common as they are in the stars that formed around our star, like Earth, which means the planets and dust that it formed out of, like our Earth, would have a much lower iron content. So if you went to stars out here, they would have a very low iron content. Their planets would likely have a low iron content. And what do we know about iron in cores of planets like ours? They create a magnetic field. And that magnetic field is very important to keeping our atmosphere intact, because our sun, just like the radiation pressure we were talking about earlier, has a lot of solar radiation that comes off it. And this solar radiation can strike our atmosphere just like it strikes the nebula gas around that white dwarf we showed you earlier. And what the magnetic field does is it reacts and actually like a force shield, and it rebounds or redirects those particles away from the gas in our atmosphere and prevents the gas in our atmosphere from being stripped away. Now, Mars has a much weaker magnetic field from us, and Mars is an example of what happens if you don't have a good magnetic field. Mars's atmosphere is much, much thinner than Earth's, something like 6% or 0.6%, I don't remember exactly. But a lot of that atmosphere that used to be there when Mars was a lot wetter has been stripped away. So if you imagine an entire cluster of stars and planets with a low amount of metal, they probably don't have a lot of strong magnetic fields necessarily on planets that are roughly the size and shape of our Earth, which means they might not have viable atmospheres at all, which means we might have sent a signal off to a place where there's no life to detect it. So maybe we're wasting our time. Of course,
yeah, that's a very good point. Yeah, if I remember correctly, and correct me if I'm wrong here, I don't know if we've even made any exoplanet discoveries in the globular clusters yet. I think there might even be speculation as to whether or not protoplanetary disks can even form in clusters like this because the stars are so close together. The gravitational interaction might pull those disks apart.
Yeah, and the reason that would be is just distance. I mean, most of the things most of the exoplanets we're finding are within 500 light years of us. You get much further than that, and they're just too far away and too close to their stars relative to us to really detect easily. So that we start to run into problems when we're looking so very far away things like this. I will have a caveat to my speech about the metallicity. That's completely me brainstorming. It was totally unscientific. There's been no study that I've read about this, so take it with a grain of salt. But that's just my crackpot theory. The second one being that without iron, they probably wouldn't have an Iron Age, so they wouldn't have the technology to pick up our signals anyway.
But maybe it would be a good place to settle if you were some crazy, super advanced interstellar civilization, because if you ended up inhabiting a globular cluster, your travel time and communication time between stars might be on the order of like weeks or months rather than years. Maybe that's a thing. Maybe
Yeah,
that's a thing. This is something I was reading about in another study about where advanced civilizations might go in the galaxy, and they might inhabit more densely clustered areas like globular clusters. and the center of the galaxy. That was from Dr. Jason Wright, if you ever want to check that one out. Interesting, just kind of, thought experiment.
Interesting, yeah. So I'm going to switch over to a galaxy now. Yeah, one other note about these dense globular clusters is the night sky would be a little bit brighter too, because there'd be so many stars. Not something like full daylight, but it would be like having the moon up even when the moon isn't up, potentially. So I'm going to switch over to a galaxy now. Now this is much, much farther away, and I'm going to clear the stacks and hopefully we'll get a good picture. So this is a galaxy that's very far away, but it is actually something you can also see with binoculars. It might be difficult to do in a city where there's a lot of light pollution, but if you're in a nice dark area and you point some binoculars up, it's big enough and bright enough that you can see it. You've probably heard of the Andromeda Galaxy. That's the closest galaxy to us. This one's a little bit further away. It's called Bode's Galaxy, just named after Johann Elert Bode, who discovered it. I'm just going to double check if I've actually got, it looks like it's centered correctly. I'll play with some of the levels here, and hopefully as we stack more images, it will resolve better. So let's try adjusting the color and then the light levels.
Some of these ones are tricky, I know, because they're either in the direction of some of the trees north of the observatory, and then sometimes some of the lights from the campus buildings as well, some of these galaxies.
Yeah, if we don't have luck with this one, we will have to switch to another target.
I know the whirlpool was on your list, and sometimes we have better luck with that one resolving.
Yeah.
Oh, I got a star in there.
You can definitely switch if this doesn't. I've got another frame stacking in a moment here. We could also increase the exposure time potentially, but
one of the other things people might note, if you're looking at this image now, you'll see that from the other pictures we've taken, there are not as many stars in this picture. And one of the reasons why that might be is that when the direction that we're looking at right now in the telescope is kind of like outside of the galaxy, where the other directions we were looking more toward like the center of the Milky Way, there's more stuff going on. So we're looking to like a more diffuse region of the galaxy. That also makes it a little bit more difficult for the images to be stacked onto each other. So if people look under the live stacking view, on the bottom left of where the image is, you'll see that it says 1 frame stacked and 3 frames ignored. And what happens is the software is actually looking for stars to lock onto between frames to be able to stack them and align them with each other. And when we can't see as many stars, it's sometimes more difficult for the software to lock on.
Indeed. So, yeah, not every image is taken in exactly the same position, and you have to actually find a star and then take the next image, which is a few pixels over, and then line up the stars like you were saying. But I'm getting warnings here, probably out of your view, that's saying that the frames kind of line. So I'm gonna switch to a brighter object that will probably be easier to see. So
yeah, we can try Whirlpool. One way, do you want to switch to that next?
Yeah, let's do it.
All right, let's do that. Whirlpool is actually Bode's is one of my favorite galaxies, and I think it has such a great profile, but it is difficult to catch. Whirlpool has a lot of stuff going on in it though, so that's cool.
Yes, it's probably my favorite to talk about. So stop me when I won't shut up.
No, never. That's why we do what we do, Kieran.
To hear the sounds of our own voices. Okay, I'll clear that frame. That bright frame was the telescope pointing at the dome. Reflected light, even though it's dark in the dome, it was enough to be really bright in that 20-second exposure. So one interesting thing is we've detected globular clusters in other galaxies. Even that Bode's galaxy we were trying to see, we found over 200 globular clusters in that. Again, in some ways it's often easier to detect things in other galaxies because we don't have all of our galaxy stuff blocking the view. Now, if you think I'm doing anything wrong with the levels here, Matt, just give me a shout.
I think we might just be pointed in not great direction again. I think this might be an effect of light pollution, but we can see. I also am seeing a bit of cloud on the view toward the AQ, so we might actually be pointed into some cloud.
We might have to pick a target in another direction.
Yeah.
Yeah, I do see some cloud in the direction we're looking. Does
Okay,
look
so
kind of
I
cloudy.
we had Triangulum on the list for galaxies. It is kind of in the other direction. We could see whether or not that shows up at all.
Yeah, that's a good idea.
I know I'm also conscious of the fact that we're almost at the end of our stream time, so maybe we'll try to get at least one galaxy in here before we wrap up.
That's a great idea. Okay, I'll switch over to the Triangulum galaxy. A lot of the weather models predicted a very cloudy night, but luckily they were wrong.
Yeah, I was
Only
for a while
slightly.
there. I wasn't sure we were going to get anything tonight. I wasn't sure we were even going to run. So, got to squeeze in those last few days we have before the fall cloudiness appears.
Yeah, now the Triangulum galaxy is one of the three major galaxies in the local group. We've got the Milky Way, which you're sitting in right now. You're made out of it. We've got the Andromeda galaxy, and we've got the Triangulum galaxy. And they're all heading on a collision course for each other. There's different models to predict the future of what will happen to each of these, but Triangulum might hit us first. It might hit the Andromeda first. We're not sure. But we don't really think it's going to be a big collision where everyone dies screaming in fiery balls of colliding stars. If you want to think of the scale of two stars, our closest star is 4 light years away. If you shrunk our star down, the sun, down to the size of a ping pong ball, that star 4 light years away from us would be like a pea 1,100 kilometers away from us. So you could sit with your pea shooter and try and shoot those stars at each other and get them to hit each other, but when you're 11,000 kilometers away, what are the chances two peas are going to strike each other? Practically zero. And it's the same kind of distance compared with the size of stars when galaxies collide. They interact gravitationally, but the actual stars themselves are very unlikely to meet each other physically because they are so small compared to the large amount of empty space in between them. So it would be like watching two clouds passing through each other. They would gravitationally interact, and they would probably change their formation. They would swap stars. Their shape would get disrupted, but star collisions wouldn't happen really in that situation. And even solar systems around stars would most likely would almost definitely remain intact. So if we were to, if the Andromeda is colliding with us, so to speak, right now, it would be happening so slowly and on such a large scale that we would not have the Earth go spinning off or hit another star or anything like that. We'd be quite safe.
I'm seeing some structure in there, Kieran.
Yes.
I think we're on there.
As the stacks improve, I don't think there's cloud blocking this one, unlike the other two, which were right next to each other. It's also one of the brightest galaxies that we can see. It has about 40 billion stars. It's not as big as ours. It's about 70% the diameter or the size of the Milky Way, but it's only between 10 to 50% as large. We are not sure how many stars in the Milky Way exactly. There's anything between 100 billion and 400 billion. Again, it's harder to count things in our own galaxy because we can't see half of it because it's obscured by the galaxy itself. But another distant galaxy like this, Triangulum, you can count the stars in it. And again, what you're looking at is our color camera. It's meant for quick images, live stacking sort of thing. It's not going to give you the same images as the other camera we have, which is designed for kind of like more like astrophotography or for doing science. And so these kind of slightly blurry images are not the best that this telescope can do. Bear that in mind. And that's why you can see more incredible images if we actually take many stacks with a more sensitive camera, and then we line them all up, and then we produce a final image. And I think, considering it is the end of the night, maybe I should just pull up an image of what this galaxy looks like with our other camera, or what galaxies look like with our other camera. Perhaps I can pull one up.
Yeah, totally. I think do we have one of Triangulum that we've cut together? I know we've done one of Whirlpool. We have Andromeda. There might be a Triangulum one kicking around.
Yeah, I don't know what folder it would be on the computer, if you can remember off the top of your head.
Well, at the very least, I know that on the desktop there's a folder there that has like a gallery.
I've got Pinwheel, Whirlpool. In there, yeah. Do you want to do Pinwheel?
Sure.
Okay, let's do Pinwheel. And I believe you took that image, didn't you?
I did not. I did do the
Okay.
pinwheel one. That one was done by Professor Howard Trottier himself. It was the first color processed image that we ever did at the observatory when it opened back in 2015.
I've got a bit of favoritism for Whirlpool, but let's do Pinwheel. Okay, let me just take a moment to add this Pinwheel, and I should be able to add this. Let me just close the one I don't want. Trying to make it visible. You know what might be easier? If I just go onto the SFU website. Oh, you know what? Maybe I minimized it. That was the problem. Sorry, the software is a little tricky. No, it does not like the Photos app, so I'm just gonna use the SFU website instead.
Okay, yeah, that should work.
I'll
if
put it
you,
in one of the live views.
Yeah.
SFU Trottier Observatory, and I should have images. Can you see that?
I might be, I think, a little bit delayed behind you, but it'll probably. Yeah, I can see. Yeah, it's coming up on the system.
So there on the left, you should be able to see the Pinwheel Galaxy, and that is that's an image that we took with our other camera, and that's kind of just to give you a comparison of that quick image you're seeing on the right is actually something you can see with the naked eye in really dark skies if you've got good eyesight. And our ZWO camera is better than the naked eye for sure, because we're looking at this in in a city full of light pollution. But if you look at the image on the left there, that's the kind of beautiful photo we can take with this with our much more fancy camera that's not meant for just live view. It's meant for really, really detailed things like astrophotography, or even counting the individual photons from stars, which can be really important for certain types of research.
Kieran, if you pull the black level over to the right a little bit on the histogram for
Yeah.
the current one, we might be able to pull even a little bit more of the arms out of the galaxy. Let's give that a try and see what happens there.
Oh, okay, cool. That works great. Yeah. Yes, now we can see much more detail. I didn't know about that. Okay, great. You can see you have driven this much before. Yes, we can see some of the arms, like you said, indeed. And that's and that galaxy and Andromeda and the Milky Way, all these three galaxies right near each other, are all spiral galaxies, just like Marcus was demonstrating at the beginning. And that's why I was asking him specifically if we were all in a thinner filament, because they all are spirals with lots of star formation going in. They aren't those red and dead elliptical galaxies that he was talking about. So yeah, it's really interesting to see all these patterns. And this is one of the beautiful things about astronomy. Things like the Big Bang, the reason astronomers are so sure it happened is it's not just one guy's crackpot theory. Different people doing different studies of different things all over space keep finding things that link to each other and confirm each other. So the Big Bang doesn't just have one piece of evidence. It has lots of different theories that match that model very well. And lots of different structures we look at confirm this Big Bang theory. And it's kind of the similar process here. When you go, okay, galaxies near each other tend to have similar properties. We look directly at the two galaxies next to us, and they are star forming, and all of these different bits of knowledge and research link in really nice ways.
Yeah, and it's a story that we'll get to tell collectively. That's the amazing thing about science. Like you said, it's not just one person's narrative. It's each of us together finding like a different paragraph of a story that we're collecting together, and it's one that we're telling across time. Like, when we said, when we're looking back at these, like the light that we're looking at right now from this galaxy, this is 3 million light years away. So this is light that came to us from 3 million years ago. And we're able to study that history of the universe across time and understand then therefore our own story within that big universe. Like you said earlier, you said we're in the Milky Way. Not just that we're in the Milky Way, but you are made from the Milky Way, that we are made from the material of this galaxy.
100%, absolutely. I think that's a really nice note to end on tonight. Unless you have any closing remarks.
I think that's great. Just again, everyone who's joined in tonight, we always really appreciate you. Thanks for coming in here, and it's always really nice to see regulars as well. And so it's nice to know that we have this family of people out there who all want to look up together and just be in awe with all this glowing hydrogen that we see out there in the cosmos.
100%. Thank you so much, Matt. Your insight is always appreciated. And also shout out to Abby and Zena, who were moderating to us tonight, and everyone who tuned in. Thank you so much.
Yeah, and a big thanks to Marcus for sharing his research with us. We look forward to the next evolution of it.
Fantastic. Have a good